That link, the first one, has a link to the slides I'm using, and there's going to be 5 Python notebooks, so you can look at those as well. These are the links. This is going to describe a course that we offered in the spring, and those are the links to the slides, the videos, and the lab site. So those are all open for people to use, and that's my contact information. So I'll give you a time to. It's basically just bit.ly pdx-SaTC24. So I'm just going to do as quick of a rundown of this course. It was offered in the spring. It's a 10-week course. And the intent, the motivation for this course, get my clicker. So as we've seen, generative AI and LLMs are changing the way cybersecurity is practiced. And the goal of this course was to look at how to change security education to best prepare students for the future that they're going to face with this deployed. And so we're looking to teach security to the Gen AI generation. And what we want to do is we want to train students to evaluate cybersecurity tasks that can be reliably automated by models. There's a lot of hype about what models can do, but what models can reliably do is much different. And one of the goals of this course is to disavow them from the hype that they might read, because a lot of the stuff that they try here in this class won't work. It fails on some of the simplest stuff. And so just for them to be able to see the thing fail over and over again is a helpful thing. So I'm going to just talk about the overall approach for the class. There are 4 main pieces. There is 1 week on models, what they are, what they can do, all the different tasks that they can perform, and how to interact with a model. So different prompt strategies. And so that's all compressed into 1 week of content because it's not an LLM course. It's just about using LLMs. And then from there, and this is what I'm going to talk about today, in order to build LLM applications, we want to be able to teach students a framework that allows them to rapidly prototype their own LLM applications. And for this, and I'm going to talk about LangChain a little bit later, we're going to have them build LLM applications with LangChain. But to do that, we have to teach them everything about LangChain that might be useful to them, and that's in 2 weeks. So it's a crash course in 2 weeks. And the 5 notebooks are just kind of like an overview of some of the 2 weeks worth of content that we have them go through. And then because we're security people, we have them spend a whole week compromising all the different LLM applications. So OWASP puts out their top 10 LLM vulnerabilities, and we want the students to see how easy it is to deploy vulnerable LLM applications. And so one of the things that we kind of trick them into doing is to deploy plausibly good LLM agents, and then they spend a week trying to get it to do nefarious things. And we'll talk about those examples later. And then from there, so that's four weeks. So almost half of the course is just LLM and building LLM applications. The rest is pointing LLMs at common cybersecurity tasks. So code summarization and analysis, reverse engineering, vulnerability discovery, and exploitation. So there was a breakout group on that just now. Command and configuration generation, code generation, threat intelligence, and social engineering. And we try and do 1 per week. And the idea is for them to try these tasks on an LLM, and then as homework, they build their own LLM application that's related to that kind of that area of task. And so that's the very end of this. Can they write reliable LLM applications to solve any of these tasks that they have chosen to try and build? And they get 1 week to do it, and they do a screencast walkthrough of their app, and they talk about what worked and what didn't work. And there's a lot that doesn't work, especially when you're using particular models. And that's another thing they find. So I'm going to just go through the different tasks, just a quick overview of the tasks that we do. The first one is code command and configuration generation. We have 2 weeks on this. So it could be just producing Python or JavaScript code based on a spec or a regular expression. So not produce, summarize actually is the first thing. So we give them some code that they might not understand, and then we ask them to use an LLM to summarize it. Try and have the LLM explain it to you, and then we give them our explanation, and we see how well do LLMs actually produce an explanation that not only they can understand, but it matches what the instructor has produced or what the code is meant to do. So that's the first week. Then we have a set of labs for figuring out configuration. So we start with host configuration. So can you explain a web server configuration, a simple Nginx web server configuration, or a firewall configuration? So simple IP tables, commands and configuration. And we'll give them what these commands and configurations are intended to do, and then they'll see if the LLM can summarize this. And this allows them to figure out, can I use the LLM as a tutor, a reliable tutor, or is it going to give me incorrect information? And then the last part is infrastructure configuration. So again, some of these students have never seen Docker, they've never seen Kubernetes, they've never seen a Terraform file. And so we tell them, here is the hello world of each one of these things. Can you get the LLM to explain it to you? And then does it match up with what the instructor has sort of like explained it to you at the intent of those files? So that's a week of the course. That week is also, the other thing that's tacked on is reverse engineering. Simple reverse engineering is another task that LLMs are being pointed to. And so one task that we have them do is to take a binary reverse engineering level in a CTF and just send it straight to the LLM, see what it can do. Another task that is really cool for LLMs to automate is just light decoding and light decrypting of code. So one of the tricks that malware authors like to do is to XOR encrypt their code with a static XOR key to evade detection. Now it's a pain in the neck and it evades detection, but this is something you could reliably automate. And the intent is that the LLM should get this right 100% of the time, but you never know. Like certain models will just completely fail anyway. Some models will get this right. And we want them to see this actually, because then you're like, oh, well, base 64, that's reliable. Most models will be like, yeah, I can just go through all your strings and then just decode all of that so that you can do the string match, the static analysis string match after the LLM has decoded those strings. A harder task, and this is something LLMs are terrible at, is deobfuscation. So they can do very light deobfuscation. So if you've encoded, for example, a string using the hex codes, it's really good at that. But if you send it through .fuscator and you ask it produce the source code from that, it has a hard time. And we want students to see that. The other thing we want to have them look at is, how do you help an LLM that is in need? The LLM is failing like crazy to solve this CTF level, and this is a very simple reverse engineering CTF level. All these CTF levels that we run in our classes, find the password that will print good job. And so the LLM will take this and it'll completely fail. But if you say, you know what, the LLM, you're not trained on assembly data. Like, who would train a model on binary data? Not many people would. They're training it on C code, Python code, and these sorts of things. And so one of the things that we want them to see is that you can transform the domain into something that the LLM is trained to look at. And that's what this part of the lab is. We're like, okay, install Ghidra, send that binary code into Ghidra, and then take the resulting disassembled C code, decompiled C code, and then see if the LLM can solve it. And then the LLM is able to solve that. And so this is an engineering pattern that you'll see in LLM applications, where you're like, hey, not only is the LLM bad at it, if I ask the LLM to do it, it's going to cost me a ton of money. And so the assembly is way bigger than the actual C code. And so you get more accurate results, and it's the token count is much smaller. And we want students to see that so that they can actually look to do that on their own. Oh, Ghidra. So that's a really common. So I started with reverse engineering games, and this is an NSA open source. They open source the reverse engineering software, and so you can just we have them install it on a virtual machine, and then the LLM application will invoke it and then send it there. And all this code is actually there. There's if you go to that lab code lab site, it's just a walkthrough where they install Ghidra, they look at the code, and then they can see that, yeah, this particular mechanism pipeline will work. Oh, it'll be at the very end as well. Yeah, yeah. Okay, so that is all summarization and reverse engineering. That's the first week of real task content. The next week is automatic vulnerability discovery, and not only that, exploitation. And so we play CTFs a lot at Portland State. So we're like, well, what are our favorite CTF levels? And I actually assign CTF levels as homework. But like, when should I stop assigning CTF levels because the LLM is better at it? And so that's one of the things that I have students do is like, hey, here are some CTF levels. We like the over-the-wire CTF levels. For web security, we also like Port Swigger's Web Security Academy, and these are free, right? Like students don't have to and the instructor doesn't have to actually pay for any of this stuff. We just point them to the levels and say, hey, get the LLM to try and solve these particular levels. And so one of the nice things about the over-the-wire ones is that there are server-based vulnerabilities where the source code of the vulnerable software is given to you. So that like the port swigger ones, only the client-side JavaScript levels, you get to see the source code. But the reason why we use the over-the-wire ones is that they actually give you the vulnerable code along with, and then you're having to look at the vulnerable code and then actually exploit the level. And so that's the idea of using these. Yeah. Natus. But actually, I had a student write an LLM agent to solve Bandit. So Bandit is their Linux CTF. And he's like, oh, the LLM should be able to do that one easily because Linux commands are like, that's a piece of cake usually for most models. So yeah, Bandit and Natus were the two. Yeah. So you can see whether or not it's good at automatically finding command and SQL injections, cross-site scripting, file upload vulnerabilities. There's a range of those levels. And then we also give them some C memory and logic errors as well. But it's mostly web stuff because it's harder to teach all the C stuff that they need to actually do those particular levels. Okay. The next week is command generation. And so we start them with just simple Linux commands, like how close are we to just a reliable natural language interface to the Linux command line? And it turns out they're using the Linux terminal tool as one of their tools for their agent. Now this is super dangerous. The Linux terminal tool is like way over way too powerful of a tool to use in an agent. And this is part of the reason why we have them use it so that they can then compromise it and do nasty things because we were like, yeah, you have to restrict the privilege level of the tools that you're using in an agent. Otherwise, we're all in big trouble because they're writing the software that the rest of us are eventually going to use. And so we show them the Linux command line, but they're like, a lot of them know the Linux command line. So like, yeah, why would I ever use this? But then so we're a Google Cloud shop at Portland State. This is much harder. Google Cloud command line, like nobody learns that. And if you go to the documentation, it's basically mountains of commands. There's like hundreds of Google G Cloud commands. And then you're like, well, maybe this is something you would want to use an LLM for. And so we give them a set of G Cloud commands and what they do. And we're like, does the LLM actually produce exactly that command when you ask it to do something? So that's the next set of labs. And then a lot of people are looking at sort of pen testing agents. So there's this pen test GPT tool where you're using LLM agents to automatically compromise machines. And so we ask them to utilize SQL map and Nmap and hash ID and hashcat and comics. And we say, can you write an agent that can orchestrate the usage of these tools to do some automatic penetration testing? And that's what this week is about. They get to test different agents doing these particular commands. And then the last one, which is kind of a fun one, is Google darking. So this is common in security, but like nobody really, I mean, I don't know all of the Google dorks, but I would like to be able to Google dork things that come into my mind. And so this is the syntax. This produces the syntax of the Google dork that you're interested in. It's actually pretty good at that particular set of commands. Okay. The next thing is configuration generation. And so one of the nice things about doing the code summarization and configuration summarization at the beginning is that then they understand those files so that when they get to the generation part, they can actually use that knowledge to see, hey, is this good at producing an Nginx configuration or a firewall configuration? And how different, like when I talk to the LLM, how different is that configuration from what I had initially intended? I'm going from what I saw 2 weeks ago, and then, but me describing what I want to the LLM, how close is the actual thing that it produces? And so we do that for Nginx and IP tables. We do it for the Docker file. We do it for Terraform and Kubernetes. And then we see, you know, can I have the LLM help me produce the configurations that are gonna that potentially might secure my infrastructure? The next one is code generation and translation. And so mostly we focus on Python examples, but we're doing things like, hey, I don't want to write my unit tests. Can you write it for me and then produce reasonable results? So if you have an older version of Python and your app is written in a pre-Python 3.6 version, you're like, you don't have type hints. And so a lot of the programming language folks are like, no, I need type hints, you know, in your code to make it readable and more reliable. And so like nobody wants to manually go and do that. And so they're like, can I actually give the LLM my Python code and say annotate it? And can this be accurate? So that's one of the tasks that they do. Another thing that people hate to do is document their code. So you're like, okay, produce the doc strings comments for my code for a particular you know, we use very small snippets so they understand what should be commented and why. But that's what they do. Another more challenging one is an algorithm refactoring challenge. And so one of the things with the Web Security Academy is a blind SQL injection level. And we give them the linear search binary or linear search blind SQL injection code. And then we ask the LLM to turn that into a binary search version that runs more efficiently. And nobody in the class was able to coax an LLM to actually do that. And you would think, like, I gave you the answer, it just does linear search. Can't you just like apply binary search to it? And at least in this current iteration, or this spring iteration, it wasn't able to. But maybe GPT-4o might be able to do this particular task. Regular expression generation is another one. And then the next is code translation. So I have a former student. She's been tasked with taking all the JavaScript code base that they have and converting it into TypeScript. And that's a terrible task to ask an engineer, software engineer to do. And this might be something that you could ask an LLM to do. And if it can do it reliably, you just saved a lot of blood, sweat, and tears from a software engineer that you actually value. So that's a lab that's in there as well. And then the last thing in this particular set of labs is a coding chatbot. So Aider is a tool that basically you plug into your repository and it analyzes your whole code base and it summarizes different trees. It uses this thing called tree sitter to give a hierarchical representation of what the code base does. And then you're able to you know, add code, debug code, and run code all in a chat interface. So you don't get to touch VS Code. And so the assignment for this week is to generate an app using only Aider. And what's nice about Aider is that every time you send something to Aider and it produces code, it automatically commits and pushes it into your Git repository. And so when I tell students, you're not allowed to edit this thing, like all the commits have to be from Aider, and then you have to show me what you wrote. This gets them to realize that, yeah, you could actually not have to manually edit code. You could just talk to a chatbot to do all your coding. But this is really hard, especially with an LLM that doesn't work very well. And we had an LLM that didn't work very well, but I'll get to that later. The next thing we have them do is build threat intelligence agents. So that AI institute that's doing Geometry, Professor Vigna's AI Institute for Threat Intelligence. We are also doing something similar. We're showing them all of these rich APIs for getting information about emerging threats. And so VirusTotal is like the mother lode of information about what's going on on the internet. So you have them, write a VirusTotal agent. Or if you're interested in a website and you want to figure out what their certificates are, their TLS certificates or their WHOIS information, can I write a natural language interface to collect all the information I'm interested in these various APIs? And at the very beginning of the class, we have them set up their own API keys on these services. A lot of them need it. And then what they can do is with their API keys, they can write their own agents as part of this particular week's assignment. The last week, we have them do social engineering. So using LLMs to produce fake content like profiles, news, and phishing lures. And then we also have them do things like build LLM agents to sinkhole things like pig butchering operations. And then they can see how an automated chatbot might help deflect some attacks away from victims and over to the LLM. The LLM will happily continue a conversation with an adversary back and forth. And I had students say they actually spent hours on this because they thought it was so fun trying to converse with this as an attacker. Okay, so before I can have students do any of these things, they're building LLM applications for each one of these weeks. I have to first go through LangChain, and this is the framework that we're using to have students build their apps around. So why LangChain? I consider this the operating system for LLMs. And I think this is as valuable of an operating systems course as our traditional the operating system course that I had, because people are writing to LLMs as just part of their application, right? And they're not writing into the file system as much as you would in a traditional operating system course. And so we chose LangChain because it really does have all of the batteries included. It's kind of like using Python. It has all of these abstractions that are super useful for building more complex applications. And then it's also open source and model agnostic. Like if you write a LangChain app for OpenAI, it's super easy to just point the LLM to another model that you prefer. And that's what I'm going to show you initially. So I'm going to start with the hello world of LangChain. And this is just interacting with a model. And so here's the hello world for Gemini. So you import the LangChain Google package, and then you import the chat model. And so for these initial hello world models, there's two kinds of models. There's the generation model interface, and there's the chat model. We're going to start with the chat model, and we're going to show you the difference between the two later on. And so you say, I want a Gemini model. So this is Gemini 1.0. I'll instantiate the model, and then I'll invoke it with a prompt. So it says, write me a haiku about Bulbasaur. So my student really likes Pokemon. So he's like, all this Bulbasaur Pokemon stuff is in this class. And then you print the content. Now, we like Google Gemini because it has large context windows. So if you're doing a retrieval augmented generation application and you don't want to actually filter out the relevant content, you just give it to Gemini. Gemini will take like 100 kilobyte of context and it'll be okay with. Whereas some of the other models will choke on like 4 kilobytes or 4,000 tokens. And so the other thing we like about Google, and so most of the labs in this class assume Google. And there's instructions on getting Google Cloud coupons. The other reason is that Google has a generous education program where you can get classrooms full of coupons without the student having to supply their credit card. So Portland State is kind of like a lower socioeconomic background school. So that matters. Like students don't have credit cards to like put up for their education like this. And so that's why we're using Google for most of the exercises. But we like to show students that if they do want to pay for it, that it's really easy to switch from Gemini to OpenAI. This is the same code. You just import a different package and a different model, and then everything else looks the same. We like using OpenAI because almost all of the code examples on the internet are using GPT as the model for their examples. We also found that for the reasoning tasks for LLM agents, it just works a little bit better. So we prefer that for some of the agents. And then it just gives you a little bit more predictable performance and results and responses than Google. We had a hard time getting predictable results with Google, but it might have changed. And then we're also now using Anthropic Claude, and this is mostly for code generation. And this came from my student who does a lot of code generation for his work. And he was like, you got to do this because it's right now, it's beyond what some of the other models that he uses can do. So I'll trust you. Okay, I'll get the Claude. And then finally, if you want to run your own model, we have a lab. The very first week, they set up their own open source Ollama server, and this allows you to host open source LLM models on Google Cloud infrastructure. So again, this is no credit card required, but you're going to utilize the coupon that Google gives you to instantiate a virtual machine that's got a GPU attached to it. And it can be hard to get that GPU. There's a lot of demand people. And so we actually have in this lab, we have them do a preemptible VM because you can get GPUs if you just say, I only need it for 3 hours. And that's what these instructions are. But once you have your server up, then all you need to do is just point the Ollama model over to that URL, and then it basically works the same as the other models. And this is why we're using LangChain, right? Because I can just replace these calls by just changing a small amount of code between them. Okay, you can even do things. So in LangChain, you could just even if you want to compare all the models that you have all at once, they have this model laboratory class. And you just, include all the models and you say, hey, write me a haiku about Bulbasaur. And then you can see all those results. So I'm going to just go to the initial Python notebook in that directory and show you what is there. So when you go on that bit.ly link, so actually this might be a good time to show you that URL again. So for people to, it's this bit.ly pdx -satc24, and that takes you to this Google Drive that you can go click. Oh, shoot. This happens to me all the time in class. I'm like, oh yeah, I forgot to. The folder, it's just the slides. Okay, yeah. All right, right there. Wait, it says that really doesn't work. Was anybody able to? Oh, okay. Oh, this one here. Okay, I'll fix that later. Yeah, yeah. All right. Um, okay, so this is the first notebook. Let me get my cursor over here. And then you can see so one of the things so all of these models, we have them access all the models in the same way using API keys. Now, if you're using Gemini on Google Cloud, they're going to want you to use the Vertex AI package and use cloud native permissions to access the models. And we intentionally did all of it using API keys. And so in Colab, there's a way of setting these API keys without giving them up to everybody. And so in order to get this notebook to work, you have to have API keys for each one of these. And so you can, from here, you can see that you can see the results. So this is Google. That's the ChatGPT, and then this is the Anthropic response. Okay. Let me go back. Okay, so the next thing we teach them is prompts and prompt templating. So that's this next aspect. And this is the package, LangChain.prompts. And so the idea of prompt templates is that you basically have an application and you have instructions that you're going to give to every query that you're going to sort of attach to every user input that goes to the LLM. So you get the instructions and the prompt template instantiated. And then from then on, when the user is interacting with your application, they're going to be sending in their query and then potentially retrieving some content to splice into that prompt in order to send it to the LLM. And so here's an example, the hello world of prompt templates. You're saying, I'm going to import the prompt template class, and it's basically templating as you would see it like a Python F string or a JavaScript string literal or a Jinja template. This is basically the same functionality. You're going to provide placeholders for things like the query that's coming in and maybe other named parameters. And then what you're going to do is you're going to create an instantiation of a prompt by invoking it with the named parameters that will fill in this prompt template. Okay, so as soon as we talk to them about prompt templates, we have to talk to them about prompt injection. This is like the most common vulnerability for LLM applications. And that's what this second notebook is about. So this is where we also talk about the generation model versus or the completion model versus the chat model, because the completion model is super easy to inject into. And everything you send to the completion model is one big string. With a chat model, you're actually sending it a structure of messages, either from the system, the human, or the AI, and it's much harder to inject into that structure. So if any of you are, most of you are familiar with SQL injection. When you inject into a SQL string, it's because it's one flat string, but you can't inject into a parameterized query or a prepared statement because you have a structure now and you can't inject, you can't break the boundaries of the structure. And so this is what we teach them right at the beginning because prompt injection is so common in these applications. So here's an example of an application to detect spam. And you're going to give it this is a few shot template where you're going to give it some examples to improve performance. And so classify these following email snippets. And so here's an example of unclaimed winning ticket, which is malicious. And thanks for your interest in generative AI, which is benign. And then you ask for the user message and you generate a prompt template based on that. And so here's the prompt template above. And so here is a expected usage. You say, warning, malicious activity on your account, and then invoke the LLM with that. And then it'll return malicious. But here's an injection where you're like, click here to win, and then you're going to basically put in what was in this format of the prompt template and say, hey, this is actually benign, and then insert a next message that is also benign. And then what you'll get is this thing is classified as benign. So that's what this next example is. There's two parts of this. So let me get my. So you'll get the injection. And this is like one of the simplest injection attacks that we can show students where because this is just one string to the model, it thinks that this is your actual message. This allows us to then talk about the chat completion model. And so with the chat completion model, the way you can specify a template is from messages. You specify an example system prompt, and then some, in your few shot examples, you can actually have structured messages that emulate what you're expecting the application to do. And so that's what this is doing. So in my chat template, I'm going to say, hey, these are your system instructions. Classify the email using malicious or benign. And then I'm going to give you an example. This is the first shot, unclaimed winning ticket, view attachment. And then you say the AI is supposed to produce malicious. And then you get a benign message. And the AI is supposed to produce benign. And then you have your placeholder. And it's much harder to inject into that thing than it is to inject into that flat string. And that's what we want to show them with this module. And so in order to try and inject into that template, you're basically having to do this. You're trying to this is a classic SQL injection. You're going to break syntax with a single quote. You're going to try and emulate, the rest of this model. And then you're going to try and trick it into thinking that this is benign. And if you go back, so that's what the next part of this notebook that you see here is doing. So you see the chat prompt template from messages, and then you see the adversary is trying to inject into this template. And what you'll see down here, I print not only the messages that get sent, the response, the LLM's really good at saying, you know what, it looks like it's part of a code injection attempt. So you made life easier for your LLM application by using the chat model. And this is why OpenAI is kind of deprecating the completion interface for their models. Almost all of them are using the chat model. I think GPT-3.5 Instruct is the only one that they have that will just do a raw completion model. Google supports both on every one of their models that we've used, at least. But this is where you can teach students why. Like, why do you want to use a chat model versus a completion model? Okay. I think that's all. I want to show you where the injection actually is trying to happen. So you see these AI messages, human messages, AI message, human message. And so here is the injection, and you see the message, click here to win. It doesn't inject into the human message. It doesn't actually, it's not successful in closing out this human message. And this is why the snippet gets classified as malicious. Okay. Whoops. Okay, so the next thing I want to talk about are chains. Complex applications often take input and output of an LLM and then feed it into subsequent stages of processing and then maybe even back into the LLM again. And so LangChain provides the facility to build sort of sequences of functions as a chain. And they use this thing called the LangChain expression language. Some people like it, some people hate it. It's what I teach, and they can take it or leave it. A lot of my students do use LCEL, but some of them are just like, just give me regular Python. They don't like, it's not Python conformant specifically. But it's a really concise way of expressing your LLM application. And the idea is that you have parts of the chain, and what gets passed to between steps of the chain is basically Python dictionaries or JSON back and forth. And so here's an example, a simple prompt to LLM example. You have the user input, it should get piped into the prompt template, and that should get piped into the LLM. And so this is the hello world of chains. You're like, okay, instantiate the model, instantiate the template, and then I'm gonna express a chain that says, when you get your input, send it to the prompt, and then send it to the LLM. And then I can invoke this chain with this dictionary that says the key subject should be associated with bears, and this is basically going to get sent to this prompt. So tell me a joke about bears, and then to the LLM, and then this is where you get the joke out of the LLM. Okay. So the next Python notebook is a program that basically has multiple prompts and then chains output from one prompt into the LLM and then back to another prompt. So this particular code will generate stories, have the LLM generate stories based on an occupation that the student provides, and then we'll test how gender biased the LLM is at producing sort of like the gender ratio that the Bureau of Labor Statistics thinks is the breakdown for that occupation. So there are two prompts here. The first is generate me a story. So generate a 100-word story, and usually after 100 words, the LLM is going to be forced to use a pronoun. It's going to be he or she. And then the gender prompt says, from the story that's provided, figure out whether or not the gender, figure out the gender of the character in the story provided. And then the output should be either male, female, or unknown. And then you're going to give this prompt something that feeds into the story. And so this is the chain that is used to express this application. I'll take the input, which is an occupation, and I'll send it into the story prompt. I'll get the result from the LLM. The LLM is going to send me back a dictionary, and I have to actually parse the dictionary and repackage a dictionary to send to the next prompt. So in the output of the LLM, there's basically a dictionary that has output.content as the result of the LLM. And I'm going to send that as part of the story key in the dictionary for the gender prompt. And then you send that to the next LLM. And then you say male or female on the other side of this thing. So that's just a toy example of using this chain. And then I can invoke it with an occupation. Okay, so let me show you the code for that. Get my cursor back. So test occupation bias. So you can see invoke the chain with the carpenter and it's male. And then you can say, I'm going to write a test occupation function where I'm going to run the thing 10 times. I'm going to run the chain 10 times on a given occupation. And then I'm going to count what genders are there. And this is where you can teach some biasing, whether one way or the other. You say garbage collector, all male, president, all male, flight attendant, all female, and these sorts of things. And this is where you can say, hey, Bureau of Labor Statistics, is this actually representative or not? And then you can see some where clearly the people training the model are shifting the results. So Google got kind of bad publicity for doing this, but you can see things like all firefighters were female. And so you can actually see some of the model dynamics. Like I think this is actually a bug in Google. This is from Gemini, I think the results here. So that's the third notebook I wanted to show. Okay. So the next thing I want to talk about is context. So when we talked about prompts, we have instructions and we have the user query, but we didn't really do anything with context. And as it turns out, one of the things that the LLM might need after training is up-to-date information. It needs to be able to incorporate new data, because otherwise you give it this question and it's like, yeah, I can't answer that. I don't have up-to-date data. And so one approach that's being used everywhere to address this is in-context learning. It's like, I have a knowledge base. I know all the information about the CS program at Portland State. I'm just going to send that in with the user prompt. I'm going to have this context-aware prompt, and then the LLM is going to use that knowledge base with this prompt to generate the result. The problem with doing this blindly is that it's super expensive. And like for Gemini is okay. Like you just give it web scrape the entire website and then just send it into a prompt. Gemini can handle that. Nobody else can. It'll choke all the other models and it's be super expensive. And so what you actually want to do is to just find the relevant documents that are related to that question and then do the context-aware prompt that's just with the relevant data and then send it to the model and then produce the result. And so the next thing we teach them is retrieval augmented generation. So rather than a prompt that goes to an LLM to an answer, what you do is you have a prompt and then you find some context. So you could either go to a stored database that you might have locally, or you could write a tool to fetch that content from the web, and then you supply that into with the LLM and then produce the answer. Okay, so these two parts of LangChain are going to help you build a RAG application. So they're the document loaders and the vector stores. And so I'm going to first talk about document loading. The data that you want is in many different documents. It's in many different document formats, and it's spread across your enterprise or the internet. So many different locations. And so you need to, as an application, be able to retrieve all of that data, extract the data that you're interested in, transform it, and then basically load it into your application directly or load it into a database that your application can access. So this is what, if you teach a data science class, this is what they call an ETL pipeline, extract, transform, and load. And you want to be able to do that. Students need to be able to do this as they're building their LLM application. But we don't want them to actually have to manually write these things themselves. And that's why we're using document loaders, because it makes it really easy to do this operation without actually having to program a ton. So this is a picture of all the different document loaders that LangChain has. It's basically a community-driven sort of part of their package. And so we can have them select any number of these things as document loaders for their application. So some of the ones that we show them are the web loaders. And so if you want to point your app to arbitrary web content, you just use one of these base loaders. The problem is it's just going to give you the raw source, like all the JavaScript, all the CSS, all the junk. And then you have to transform it because the LLM doesn't want to see that. Or you get terrible results if you just take that and send it into the LLM. And so almost all of these things, you have to extract the text or write your own parser. So for example, for Drupal, we parse the article tag because we know that's where all the good stuff is in a Drupal site. So that's the idea. There are many loaders for very specific sites on the internet. People are integrating Wikipedia into their LLM applications so often that Wikipedia is like, we don't want you to write your own scraper. We'll give it to you. We have the structured data before it gets formatted for the web. We'll just write this loader that ships it to you directly. And then there's all sorts of document loaders: text, PDF, Microsoft Word, Markdown, and CSV. And so one of the things about this that we also talk about is when you get this content, you might need to split it up into chunks because some of these documents are large and the LLM has a context size and it's not going to want to like just take your whole document. And so you have to be able to split it into chunks to reduce the context that's sent to a model. And so I'm not going to cover that in this particular talk. The next thing you need to do is if you're going to store this content for fast retrieval, we teach them about vector databases. So ever since LLMs were released, there's been a cottage industry of vector database sort of companies that are out there. And so these are specialized databases that help us to build a RAG application efficiently. And so the idea of a vector database is that rather than in a traditional database where you just store the data in the database, you basically, with the data, you store a vector that is a semantic representation of the data into the vector database. And then this is what happens. You have your documents, you split it up into chunks. And then with these chunks, you basically will call an embedding model, and this will vectorize. It'll take your original data and produce a semantic vector that describes your data. And it's a wide vector. And then from here, you store it into the vector database up here. And then based on where you are in this vector store, it determines where you are semantically, where your semantic content is. So then what you can do is you can do a similarity search. And this is what they're really sort of known for. If I have some other document and I have its vector embedding, I can return all of the other documents that are semantically close to this particular document and given its embedding. And so this is going to help us because if we have done our document loading and loaded it up into a vector store, then what we can do is when the user is asking a question and we want to find the relevant document to answer that question, then what we do is we take the user's question, we call the embedding model to get the vector, and then we do a similarity search in this vector store to find the content that we need to, the context that we need to attach to this question to then send to the LLM to get it answered. And so in this case, let's say the embedding pops up, and you can't, the colors don't match up that well, but the yellow is right here. So then this is where the embedding for the query is. And then the vector store is going to return the red dot because it's semantically closest, and then return the relevant splits. And that's what you use to send into your RAG application. Okay, so then, so this is it, and just speeding through this. So you create all the vector embeddings from all the documents that you have loaded. And these are the vectors that you see here. You insert it into the vector database, and then you have a user asking a question, and then you get the prompt embedding. And then you query the database with the prompt, and you get the relevant documents for that query. And then you create that context-aware prompt by splicing these relevant documents into that prompt template that you had earlier. And then you create the context-aware prompt, send it to the language model, and get the result. Okay, so this is the simple RAG chain. You have to explain all that other stuff in order to have this make any sense. So this is the template you're using. Answer the question based on only this context. Create this template, create the LLM, and then instantiate the vector store. And we're using ChromaDB for this thing. And so there is this retriever object that basically does the similarity search for you. And so then you construct the chain. You get the relevant context using this retriever and given a question. And then you splice that into the prompt, goes to the LLM, and then you pull out the output, and then you get the answer to that. Okay, so I have 5 minutes, so I'm gonna skip the fifth one, but I'm gonna go through just this fourth notebook. So this is the document Q&A lab. So we have some URL content. We have the Wikipedia content, which is the LangChain entry. We have a DiskPy preprint archive paper for that loader. We have a text file, the US Constitution. And then we also have this Bulbasaur Pokemon information. And we embed an indirect prompt injection attack in this Bulbasaur. And then the next week after they do this lab, they'll see that this actually causes one of their agents to execute a terminal command. And then they get scared. They're like, oh, I don't want to run my agent anymore because of this. It's unpredictable what can happen. A PDF file that we use is the Python cheat sheet, and then the Word file are famous quotes from different authors. And then we have a CSV file with serial nutrition data in this example. Okay, and so this is their first major language application. So again, I'm going to walk through this. You have the splitter to chunk up the documents. You have all the loaders that we're using. And this is how easy it is to just add different things to your pipeline. And then we're going to use Chroma as the vector database. And then for the embedding model, this is also a language model. We're going to use the Google's generative AI embeddings. And then we're going to instantiate the vector database using this embedding model. These are tightly tied to each other, the embedding model you use and the database that it's instantiated with. And then you have a persistent directory where you're storing all of this stuff. And then we have this generic load document function that just basically splits up the documents that it gets into chunks and then just simply adds it to the data store. So this is adding all your documents. And then they see this. This is how easy it is to load all the different data formats into that vector database. URLs, Wikipedia, archive, etc. And then, so that's basically loading all the documents. And then we give it the data that we're going to use to load those documents. And so these are the things that I just mentioned in the previous slide. So all the different content and in the repository for the class, which you can clone, this is where we have the different text files, PDF, docx's, and CSVs. And then what they can do is they can define a function that searches the database. And it just says, based on a query, find me the relevant documents that will answer these questions. And you'll see that the results come back with the source that closely matches. And then finally, we are going to basically invoke a query database function where the query database will not only retrieve the documents, but will splice it into a chat prompt template that includes the context and the user query. And then this RAG chain is similar to what you saw before. And then we have them run the actual queries to produce the results. So I'm going to walk through this quickly and then wrap up. And skip the agent stuff. So this is the loading code. And then you can see when you go and search the database, well, it just basically says these are the data sources. After you do the loading, there's a metadata field. Every time you do a load into the vector database, you can set the metadata field to get the actual source that you're retrieving the content from. And so that's what this is. I'm dumping out all the content in the database by the metadata that's associated with it. And then this is the search DB. And so you can say, oh, who created LangChain? And it knows that the closest document is the Wikipedia URL or DiskPy. and it knows that it's from the preprint archive. And then when you do the search, you'll see that the actual results are accurate. So that's what we want. We want students. They actually have a RAG application for doing threat intelligence in week 8 or 9. And we use this exact same code for that one. We just point it to threat intelligence research rather than Pokemon information. Okay, so with that, I'm going to go to the end. Let me see. I'll just skip through the agents. The agents is the last thing that we do. So there's basically 2 weeks worth of all this LangChain stuff. But with the agents, one of the things that I wanted to mention is that this is super vulnerable code. And we want to show it to them up front, because if you give an agent that code, you're done. And so like this is like if you're actually they actually deprecated this this pattern because people were using it. But this is like getting, basically a nuclear weapon that you're giving a developer without any safeguards. And so then we show them how to build secure tools. How do you restrict the functionality so that the agent can't be, if it does get compromised, can't wreck you? And that's what the secure tool design module is. And so I'll fix that link for the slide material. That is a YouTube channel. I want to talk a little bit about the labs. I have 1 minute. So the labs are here. You see it's a website, and this is using Google's CodeLab format. And the one thing that I love about Google's CodeLab format is that I can generate all of this stuff using a Google Doc. And so in case you're interested in this, basically every one of these things, if you click on one of these labs, you'll see this responsive step-by-step lab walkthrough. And if you see this report a mistake, I have my students do this. If they have a mistake in this lab, they click on it, and that points them to the Google Doc that has been used to generate the lab, and then I can fix it. I highly recommend this because, continuous improvement, continuous deployment, stuff goes out of date very quickly. Like I thought the cloud was moving fast. The LLM stuff is moving faster. It's like basically I have to redo a lot of this course in a month because a lot of the models are different now, and some of the LangChain things have changed. But the Google Doc format allows me to crowdsource the development of this to students. Okay, so I'm going to end there. Thanks for coming to my session and for staying, actually. Yeah.